Enrico Fermi's famous question, "Where is everybody?" functions as a rigid empirical data point. The silence of the night sky is an observable fact. Because electromagnetic signals propagate at a fixed speed, we observe our galaxy through a strictly defined boundary, a 100,000-year past light cone. This means that we currently have access to the entirety of galactic history, spanning the past 100 millennia. If any technological civilization broadcasted detectable signals from anywhere within this geometric volume during that time, those signals would mathematically intersect our present position. Humanity has built massive infrastructure and dedicated decades of all-sky surveys to capturing exactly these kinds of artificial electromagnetic signatures. The result is absolute zero. We have a complete null detection across the entire dataset. This complete absence of contact is a mathematical boundary condition. It dictates severe physical limits on how long technologically intelligent civilizations actually survive. A 2026 astrophysical analysis by Rahvar and Rouhani isolates exactly how tight these survival limits are. This graph maps their primary statistical conclusion. The y-axis tracks the expected number of coexisting civilizations, which we call n. The x-axis measures their average lifetime, L. By reverse engineering the variables that populate this grid, we can map out the mathematical boundaries of our own future. We establish our current observational baseline right here, at n equals 1. This represents us, a single technological species alone in the galaxy. Any statistical model that pushes this value significantly higher than 1 directly contradicts the physical reality of the empty sky we observe. To populate this graph, the researchers utilize a modified version of the Drake equation to calculate how many civilizations should exist right now. The equation states n relies on 4 distinct variables. The first component is NH, representing the raw number of Earth-like habitable planets in the galactic disk. Relying on modern astronomical data, the paper estimates this parameter at approximately 1 million habitable planets. Next is LS. This is a strict temporal variable. It represents the maximum duration a host star can support a planet in the habitable zone before stellar evolution permanently disrupts the climate. We can measure this limit locally. Changes in our own sun's solar flux dynamics dictate exactly how long Earth can maintain liquid water. Based on the paper's data, the total habitable lifespan for our sun is physically constrained to roughly 5 billion years. These astronomical numbers provide a rigid physical stage. But the true variable determining the outcome of the equation is biological. That variable is F. It represents the compounded mathematical probability that a habitable world inevitably develops life, evolves intelligence, and yields a technological society. The researchers first test a highly optimistic scenario, setting the probability of F to exactly 1.0. Satisfying this requires immense evolutionary timescales. On Earth, the journey from simple cells to industrialization took nearly 4 billion years of continuous selection. Achieving this technological plateau does not guarantee societal longevity. Complex systems are inherently fragile. They face rapid collapse from resource depletion, climate interference, and internal conflict before they can diffuse across the galaxy. If we assume the optimistic scenario is true, that biology always leads to technology, the galaxy should be saturated with overlapping species. That creates a direct conflict with our empty light cone. We can resolve this paradox mathematically by returning to the plotted data. This chart shows the specific trajectory of the optimistic probability model. The solid blue line tracks what happens when F equals 1. It maps a simple algebraic relationship. As the lifespan of a civilization increases on the x-axis, the expected number of coexisting civilizations increases on the y-axis. To reconcile this model with the reality of being alone, we trace the blue line down to where it intersects our observational threshold at n equals 1. It hits precisely at the coordinate 3.7. Solving for 10 to the power of 3.7 translates this coordinate into a hard lifespan of approximately 5,000 years. The blue shaded region dominating the upper half of the chart defines the mathematical consequences for any civilization living past that point. If civilizations under this optimistic model routinely survived longer than 5,000 years, the number of coexisting species would mathematically skyrocket into the tens or hundreds. a skyrocketed n value is empirically false. Our past light cone is completely devoid of their signals. The math yields a stark conclusion. If intelligence emerges frequently, the vast majority of those civilizations must self-destruct within just 5 millennia of industrialization. We must also address the spatial constraints. What are the physical requirements for multiple civilizations to successfully overlap and actually find each other? This map visualizes the diffusion equation. The distance between any two intelligent species equals the galaxy's radius divided by the square root of n. Setting the galactic radius at roughly 30,000 light-years, researchers assume an advanced civilization could manufacture spaceships traveling at 10% the speed of light. For context, humanity's Voyager probes have traveled for 50 years and haven't covered even a fraction of a single light-year. Even at 10% light speed, calculating the minimum physical diffusion time to cross the distance between two coexisting civilizations yields roughly 200,000 years. Whether searching physically or waiting for electromagnetic signals, two technological civilizations can only discover each other if their lifespans drastically exceed a 100,000-year threshold. The source material highlights a significant numerical tension. Physical contact requires civilizations to survive over 100,000 years, yet the optimistic biological model caps their lifespan at just 5,000 years. The source data solution is the orange line, plotting the f equals 0.01 parameter. Dropping the probability of technological emergence drastically alters the constraint. Tracing this trajectory shows a civilization's lifetime can extend millions of years while remaining below the empty sky threshold. Biologically, this means that the evolution of an intelligent, communicating species is an exceedingly rare anomaly, not an inevitable outcome of a habitable world. A technological civilization can achieve a geological lifespan only if it is statistically and physically completely alone. The source data synthesizes into a strict mathematical bifurcation. If intelligence is common, the mathematics of the Fermi paradox constrain those civilizations to rapid self-termination. If a civilization manages to be long-lived, the math dictates it must be incredibly isolated. The researchers emphasize that these results represent hard statistical upper bounds, constraints derived from the geometry of spacetime and our current observational limits. The absolute silence of the night sky guarantees a single physical reality. Surviving past our technological infancy requires us to be the rarest of